All right, and welcome back to Math 160. We are going to continue working through our Chapter 8 notes. We are going to look at one more practice problem for 8.1, and then we're going to move right into 8.2, which is estimating a population mean. Notice that we were working with proportions this entire time. So let's finish off practice number 4. Switching over to my notes. As a recap, we were told of 400 randomly selected nursing students, 35 said they planned to work in a rural community. We had a Minitab printout. Notice the information that we were provided. So these were our descriptive statistics. We were told the 95% confidence interval for the true proportion was within this range. So when we write our confidence statement, it looks very much like this statement here. So we tried to use this language again and again and again, and we did successfully all of our last class last week. So we wrote, we are 95% confident that P, our true value of the population proportion of nursing students who plan to work in a rural community, notice the language we're using again, will be between 0.060, we rounded to 3 places after the decimal, and 0.115, same thing, rounded to 3 places after the decimal. The next thing it says, can we safely say with 95% confidence that at least 10% of nursing students plan to work in a rural community? How we're going to do this is we're going to write a statement that I think will help make things clear. So first off, let's highlight or underline at least 10%, right? At least 10%. So they're basically asking the question, we're looking at, is the true proportion at least, which means that value or greater, at least 10%, right? So that's kind of, that's what we're looking for. Now, I want you to look at your bounds, look at your interval, right? I want you to look at, we're trying to figure out if the true proportion is greater than or equal to 0.10, but look at the lower bound. So we're going to answer the question, is 0.059809 greater than or equal to 0.10? Obviously not, right? The answer to this will be no. So because this is not the case, we cannot safely say with 95% confidence that at least 10% of nursing students plan to work in a rural community. Okay, we notice we have a value much smaller than that 0.10%. We see that 0.10 is within the range, so it doesn't capture all of the values of our interval. That 0.10 does not capture. Plus, it's suggesting that the true proportion is greater than or equal to 0.10. No, we can't say that. We have values that are smaller. We're going to do one more, which is part C. Practice 5 and 6, they're exactly identical. So when I fill in these notes and upload them into Lumen, you will see 5 and 6 filled out. I urge you to try those on your own and see if your answers align with mine. Part C, can we safely say with 95% confidence that at most, highlight this please, at most 12% of nursing students plan to work in a rural community. So the true population proportion at most means less than or equal to. So let's take a look at our interval again. we see that our upper bound is 0.115191. So we are going to say is 0.115191 less than or equal to 0.12. Yes, it is. So because this is in fact the case, we can safely say with 95% confidence that at most 12% of nursing students, and we finish the statement, plan to work in a rural community. And we are done. Like I said, go ahead and give 5 and 6 a shot on your own. And when I upload our completed notes, you can verify and see how you did. Excellent. I'm going to go ahead and turn a couple pages so that we can move right into 8.2. See, number 5, same exact thing, write a statement, can we safely say? And then number 6, write a statement, can we safely say? So it's the exact same thing, which is why I have no problem moving forward and looking at 8.2, estimating a population mean. All right, let's get this going. I would love a volunteer to get started with the reading. And what I'd like you to do is actually just read this entire first section here. So volunteer, please.
I can do it.
Thank you.
If I don't cough, excuse my decongestion. All right. Properties of a student's T distribution. Has a mean of 0, is symmetric about the mean, forms a family of distributions, each with a different degree of freedom. DF equals n minus 1. The population standard deviation is unknown. Has a variance greater than, is that I or 1? 1. Okay, sorry. But as the degrees of freedom increase, since n is increasing, the variance approaches 1. Oh, I'm out of breath. As the number of degrees of freedom increases, the T distribution will approach a standard normal curve.
Perfection. Very, very nice. So essentially, there's a few things going on here. So we're going to be learning how to estimate a population mean when the population standard deviation is not known. So this statement here that Lainey read, I'm going to highlight this. This is really important. Okay, when the population standard deviation is unknown, we are going to use the process in this section to estimate a population mean. That's really important to note. That's what we will be doing in this section. It's also very important to understand that as the number of degrees of freedom increases, which by the way, degrees of freedom is n minus 1. We know that n represents the total number of items in our set. So it's going to be 1 less than that. So if we have 30 people in our sample, well, then the degrees of freedom are 29, right? It's just going to be 1 less. As it increases, the T distribution approaches a standard normal curve. Notice here, when we have our T distribution of n is equal to 5, it's a very small sample. Notice how spread out these values are. When our T distribution n is equal to 17, notice it continues to get closer and closer to the standard normal curve. The more degrees of freedom we have, the closer to standard normal we get. Okay. So let's check this out. Using a table to find critical values. So let's use a table on, and really what they're referring to is the table at the very end of our packet. So take a look at the last page of your notes. You have the T table for your critical T values. Notice in this first column, you have your degrees of freedom. Then notice we have the columns referring to the area in one tail or the area in both tails. But this should actually make sense. So think about it this way. If the area in both tails were, for instance, 20% in both tails combined, if it were 20%, then what that means in one tail is there's 10%, right? Does that make sense? When we think about it like this, I want you to consider the fact that we're referring to 80% confidence interval, which may help if we write that here. If we want to bound the middle 80%, then there's 20% left over with 10% in each tail. I'm going to say that again for a different one. Notice here the area in two tails is 10%, right, combined. So that means in each tail, there will be 5%, which refers to 90% confidence interval, or that middle 90%. I'm going to fill each of these out. So this is the middle 95%. Here we have the middle 98%, and here we have the middle 99%. It may be helpful if we write those intervals in there or those percentages in there so that we can be very clear about what it is we're finding. Good. So let's go back to this question. We're going to keep our table handy, so definitely just leave this aside. We want to use a table to find the critical values that bound the middle 90% of the area under the curve with degrees of freedom 19. This is very, very interesting. So we want our degrees of freedom to be 19. And we want to bound the middle 90%. So we want to look at the critical values. So let's go to our table. We're going to look at degrees of freedom 19 with the middle 90%.
1.729.
Yeah, let's take a look. Boom, there it is. I'm going to go ahead and, you know what? I'm going to highlight it so that I'm not writing all over the place. Let's highlight this value, 1.729. Notice it's the middle 90%, degrees of freedom 19. Perfect, that's our critical value. So what we can do now is we can actually plot that critical value. Now, because it's the middle 90%, you're going to notice we'll have a positive and a negative of that same value, just like we did in unit 6. 1.729, that's approximately here. 1.729. Our critical value is equal to 1.729, and we are going to also identify its opposite, which is negative 1.729. Draw our dotted line up, and we are referring to this middle 90%. And that's how you find your critical value. Let's go ahead and turn the page. By the way, just to kind of reiterate what we've learned before, if the middle is 90%, we know that in each tail, there's going to be 5% left over with 10% altogether. Good. Let's turn the page and try another one. Practice 7. Find the critical values that bound the middle 98% of the area under the curve with degrees of freedom 57. Note that if your degrees of freedom is not on the table, use the closest degrees of freedom. What are your thoughts? Talk to me about what you're thinking when you look at this chart. What are you seeing here? First off, which column am I going to be locating my critical value in?
The second one.
Definitely. We're looking at the middle 98%. Now, what we're going to do is we're going to follow this all the way till we see a degrees of freedom 57. But we don't have that option. So we want to go to the closest one. That's going to be degrees of freedom 55. We're only 2 away from 55 versus 3 away from 60. So our degrees of freedom will be our critical value will be 2.396. Stop me if you have any questions whatsoever. I would love to help out if there are any issues. So 2.396 and negative 2.396 as well. And then we shade this middle region. And this is the middle 98%. I'm going to write out my critical value is equal to 2.396. Any questions for me on that so far? Cool. Okay. Do you remember in our last section when we had a procedure to construct a confidence interval, but this was for the population proportion? So here's for estimating our mean when our population standard deviation is not known. Remember that mu represents the population mean and sigma represents the population standard deviation. I don't mind writing the labels out again just to make sure that we're okay. Suruchni.
I have a question about the same thing. When we find the negative 2.3 and a positive 2.3, do we have to do the same thing where we subtract the bigger value from the smaller one and that would be the answer, or just the critical value would be 2.396 would be the end of our answer?
Yes, the 2.396 is that particular value that you're going to need to evaluate the margin of error. So what we're actually going to do is we're taking this information just like we did with our population proportion. So we end up saying, okay, does it meet certain requirements? That's the first thing. The next thing we say is, what's the margin of error, right? Because we're looking for that confidence interval. We want to find an upper and a lower bound. So we have a specific formula for the margin of error in this case using the t-distribution. We then say, okay, well, we want to estimate the population mean, so we're going to use the sample mean to do that. And remember how in the last one, we had our proportion, we added the mean and we subtracted the mean? And that gave us like a lower and an upper. For that time. Yep, same thing. That's what we're doing with this particular critical value of our t-distribution. So we're going to go through that same process, just like we did with estimating the population proportion.
Okay, so we have to do that, the rest of that. We have to add that into this.
Oh yeah, it's going to be like that multi-step process. So, but it's nice because it looks kind of identical. It's kind of like, you know, okay, we're doing it again. So no big deal. You'll see.
It's good. It's actually bringing back, like making it easier for me to understand the path. Yeah.
I also love the fact that it is so similar. It just kind of allows you to feel more at ease with following that same kind of process, like the bigger picture. You find the margin of error, and then you find your lower and your upper bound, and then you write a statement that tells what that means. Same thing, same thing. Awesome. Let's check it out. So remember how we talked about on your formula page, you really want to have everything laid out, written out, described with labels, all that kind of stuff. This is going to go on your formula page, just like before with the population proportion. Okay, you're going to want this procedure on your formula page. So the first thing you do is you verify the requirements. Is your sample a simple random sample? Are the following conditions satisfied? Now you either have to have one or both. If you don't have to have both, you really just need either or. So you're either told that the population is normally distributed, the population from which the sample came, or you see that your N, the number of items in your sample, is greater than 30. As long as one of those conditions are satisfied, then you can use this procedure to construct a confidence interval estimate. We then move on to the margin of error. Notice the formula. So to calculate error, you have your critical value, and you're going to multiply it by the sample standard deviation. Remember, we don't know the population standard deviation. So the sample standard deviation divided by the square root of n, the number of items in your set or in your sample. You're then going to find the values of the interval limits. So again, we typically use this first one, right? We write it as a compound inequality. So your sample mean minus the error, and your sample mean plus the error. So just remember that. S is your sample standard deviation, and X bar is your sample mean. Okay, we're going to use this information. We'll round to 3 significant digits, just like we did before. And then, of course, we write our confidence statement or interpretation. So let's try that. I'm going to keep my T-table handy. So I'm just going to set this aside as we turn the page to look at practice number 8. A vice president in charge of sales for a large corporation randomly chooses 110 salespeople. What does that value represent? Shout it out.
Population.
A little bit.
N,
N, yeah, yes, good. N is equal to 110 salespeople. That's something I want you to kind of jot down as soon as you read it. I also want you to notice that it says randomly chosen. Okay. Randomly chooses 110 salespeople and asks them how many contacts they make per week. The sample reveals a mean of 20 contacts. The sample reveals a mean of 20 contacts. What notation would this represent?
X bar.
Yes, X bar. X bar is equal to 20. I love it. With a standard deviation of 3.5. What's the notation for this?
S.
Yes, S is equal to 3.5. Perfect. Because we're referring to specific numerical values that describe the sample. So these are the sample statistics. Good. Construct a 98% confidence interval estimate for mu, the true mean contacts per week a salesperson makes, and write the confidence statement. Good. So one more thing I'm going to write down here because we're using the T distribution. If you know that your your sample has 110 people, your degrees of freedom will be 109. One less, always one less. So the first thing we note is that we meet the random requirement, which is really nice, but we also meet the second requirement that N is greater than 30. So we definitely can go through the process of constructing a confidence interval to estimate the true mean. Next, we want to look at the critical values. So you're going to go ahead and look at your chart, your T distribution. Notice we want to construct a 98% confidence interval. You know your degrees of freedom are 109. So taking a look at the chart, what do you see here is your critical value? Shout it out.
2.364.
Yes, that is correct. So I'm going to show you the table in just a moment. We're going to use the notation that we were provided for writing the critical value, and that was 2.364. If you're still unsure as to how I got this, let me show you the T table for a moment. Remember, it's a 98% confidence interval with degrees of freedom 109. So you go to where you're looking at 98%, go all the way down to 109. There is no 109, but the closest is 100. So our critical value is 2.364. I'm going to go ahead and highlight that value so that you can see it on the chart. We always go to the closest one. Beautiful. Now we're going to calculate the margin of error. As a reminder, the formula to calculate margin of error is E is equal to, you're going to take your critical value and you're going to multiply it by the sample standard deviation divided by the square root of n. So we're going to plug in all of our values. E is equal to, we know our critical value is 2.364. And we're going to multiply that by the sample standard deviation, 3.5, divided by the square root of n, and n is 110. Please don't mix up the degrees of freedom with your n. N is simply the number of items, people, etc. in your sample. Go ahead and take your calculators. I'm going to do the same thing. And let's just all punch this in. I'll give you just a couple minutes. And why don't you tell me your margin of error, and for now, we'll round to 4 places until we write our confidence interval statement. What are you getting?
I got 0.7888894.
Yes, I love it. I love it. So we could just leave it as is. I'm going to round to 4 places just so that we're not rounding too much before we find our exact confidence interval. Round it to 3 places. So we have 0.788, and I'll round to the 4th place, which is 9. Thank you, Surujini. Perfect. Next, we need our formula for the confidence interval, that compound inequality. And thank you, Mike. I see your answer in the chat. Perfect. So from our previous page, we saw that we are going to take the sample mean and we're going to subtract the margin of error. And that's going to bound the true population mean along with the sample mean plus our margin of error. So we're essentially just going to fill in these values. We know from the word problem above that our sample mean is 20, which is nice. We write all this information down as soon as we see it. So our sample mean is 20, and the margin of error is 0.7889. So we're just going to go ahead and fill this in and calculate our values. We want to round our answers to 3 places after the decimal. What is your lower bound?
$19.2111.
Yes. So I'll just round to 3 places after the decimal, 19.211. That's perfection. And what is your upper bound? Anyone?
20.789.
Perfect. And we have our confidence interval. We can also write it in interval notation, 19.211, comma, 20.789. We can write it in interval notation as well. Perfect. Thank you, Emma. So interpretation. It's going to be essentially the exact same thing we did with estimating our population proportion. So let me write it out so you can see that it's actually really, really closely related. So we are 98% confident that mu, our true population mean, for number of contacts per week will be between 19.211, and 20.789. See, it's pretty identical to the process we did last time, which is really nice. Good. Very cool. All right, let's turn the page. I would like you to do practice number 6. I would actually like you to work through the entire practice number 6. So I'm just going to give you a few minutes to do so. Once you have this completed, all I would like from you in the chat is your confidence interval interpretation. So I would love your answer for part E when all is said and done. All right, take a few minutes to do this. I'm going to pause the video as we work. Okay, so let's go through the process. The first thing you notice is that there were 63 randomly selected people. So we're going to say N is 63. I'm also going to put a little check mark next to random because that's really helpful. So these people are 30 years and older. They're asked, how many hours of TV do you watch per week? We're told that the sample mean, X bar, is 15.65 hours. We're definitely going to note this with a standard deviation, S, of 2.09 hours. We want to construct a 99% confidence interval estimate for mu, the mean hours a person 30 years or older watches television per week. It's nice because you can actually use this language in your description. And then, of course, we write a confidence statement. So we meet both requirements, that we have to have a simple random sample and that N is greater than 30, which is really nice. I'm going to note here that my degrees of freedom are going to be 1 less than my sample size. If my size is 63, Jenny, that's perfect. If my sample size is 63, my degrees of freedom are going to be 62. It's going to be 1 less. So again, note for our critical values, we're looking at the 99% confidence, right? So we're going to go to the very first column in our chart, which we've labeled 99%, and we want degrees of freedom 62. So we're going to find the closest one. As we scroll down, we see that the closest one is a critical value of 2.660. 62 is closer to 60 than it is to 65, which is why we use 2.660. So we just essentially align those. So I'm going to note here that my critical value is 2.660. Next, we want to figure out the margin of error. Again, our formula is to take that critical value and multiply it by the sample standard deviation divided by the square root of N. When you plugged in your values, you had 2.660 times 2.09 divided by the square root of N, which is 63. When you punch this into your calculator, you should have had to 4 places after the decimal 0.7004. Next, we're ready for our confidence interval that follows the formula. The sample mean minus the error is less than mu, which is less than the sample mean plus the error. So you want to find each of these bounds. So your sample mean is 15.65. We're going to subtract the error. So again, this follows the same format as finding the estimate for the population proportions. The same exact idea. We're going to go ahead and both subtract and add on either side. So we should find that our lower bound is 14.950. And your upper bound is 16.350. If you wanted to write it in interval notation, you'd simply use parentheses to denote that interval, that range of values. And lastly, we are ready for the interpretation. And here's what I would write. You all did an excellent job in the chat, by the way. We are 99% confident that mu, our population mean, our true population mean of hours of TV watched per week by 30, I'll just write 30 plus, by 30+-year-olds will be between 14.950 and 16.350. I don't need the label of hours here only because I clearly identified that mu represents our population mean of hours of TV watched per week by 30+-year-olds will be between 14.950 and 16.350. And that concludes this problem. What questions do you have for me that I can help with?
For the one that I told you, would it be a problem that I didn't say the mean of hours of TV watched?
For that practice number 6, you just want to make sure that for this one, for practice 6, that you use the language of true proportion of adults that feel vulnerable to identity theft.
Oh no, I'm talking about this one.
Oh, I see what you're saying. Okay. If you didn't put the hours in here, just make sure you write it at the end. So we'll be between 14.950 and 16.35 hours. That would be fine.
I'm talking about like saying TV watched per week. Would it be a problem if I didn't add that?
No, not really. Not really. It wouldn't be a problem. Like I wouldn't take off points if you didn't write TV watched per week. As long as you had the units in there. But as thorough as you can be, you definitely want to be super descriptive. What I would do if I were you, I would look at this statement, the mean hours a person 30 years or older watches television per week, and I would just duplicate it. I would
Sounds good.
Yeah, I would just repeat that. Awesome. Very cool. Sorry it took me a while to understand.
Oh, good.
It's Monday. All right, awesome. Let's turn the page and look at a Minitab printout. So practice number 10. Essentially, we're doing that same exact idea. Okay, check it out. Let's interpret the following Minitab printout and answer the parts that follow. So it's a one sample T distribution, length of rivers in miles. We have the following descriptive statistics. You see that N is 31. You're given the mean, the standard deviation, and then you're also told it's a 95% confidence interval for mu. So you're actually given this information here. What I'd like us to note first, that if N is 31, our degrees of freedom is going to be 30. If we are looking at the 95% confidence interval, go to your table. Would you find your critical value for me?
.042.
Yes, 2.042. So your critical value is 2.042. So we still have our setup for when we would draw the normal distribution. And because T is large enough, it estimates a normal distribution. So we can label it as is. So we have 2.042 and of course a negative 2.042. So these values bound the middle 95%. It's oftentimes nice to just have all of that information here. So we're going to write a confidence statement. We are 95% confident, right? We have this information already provided to us. We also know that mu represents the mean length of rivers in miles. Okay, so we are 95% confident that mu, I'm going to write an additional statement here, so give yourself some room to write quite a bit. we are 95% confident that mu, the mean length of rivers in miles will be between 924.6 and 1,315.8. Now, remember, we're referring to miles. So the mean length of river in miles will be between 924.6 miles and 1,315.8 miles. I'm going to write an additional statement here. Something for you to consider. Also, if we were to randomly choose many samples of size 31, right, has the same size as our sample here, then 95% of the samples will have captured the true population mean. Good. I definitely wanted to include this statement just for you to kind of get a sense of what's happening here. If we collected many samples of size 31, we can actually be, we can say that 95% of those samples will have captured the true population mean. Those things go hand in hand. So I definitely want you to have that information. Good. For part B, it says, can we safely say with 95% confidence that the mean length of rivers will be at most 1,320 miles? So the mean length of rivers will be at most means less than or equal to, right? No more than 1320. So can we say this? So what we're going to do is we're going to look at the upper bound of our interval, which is 1315.8. And we're going to say is 1,315.8 less than or equal to 1320?
Yes.
Exactly. And we're going to say, yes, it is. So let's write down. With 95% confidence, we can safely say that the mean length of all rivers will be at most 1,320 miles. So it's helpful to write that inequality, right? That mu is less than or equal to 1,320. That's what that says, that the mean length will be at most. What's the inequality for part C? Let me read that first, and then I would like you to tell me what the inequality is for part C. Can we safely say that with 95% confidence, the mean length of rivers will be at least 930 miles? How would I write that? At least. What should the notation?
Below.
Greater than or equal to?
Yeah, greater than or equal to. Very nice. If you're saying that that mean length has to be at least 930, that means 930 or more, right? So mu is going to be 930 or greater. So we're going to look at the lower bound and we say, is 924.6 greater than or equal to 930? And we're going to say, absolutely not. Same thing, cookie cutter. Let's write our statement. With a 95% confidence, we cannot safely say that the mean length of all rivers will be at least 930 miles. I'm going to write that out as you do as well. With 95% confidence, we cannot safely say that the mean length of all rivers will be at least 930 miles. Turn the page when you are ready. Part D still addresses our previous practice problem. Can we safely say with 95% confidence that the mean length for the rivers will be at least 900 miles? What's the statement we're going to ask ourselves? What is our follow-up statement here? Is
900 less than or equal to 924.6?
yes, I'm going to switch the order just because we have the mean first, greater than or equal to 900, but you're absolutely correct. You said it correctly. So is 924.6 greater than or equal to 900? And we're going to say yes. So then we can write our follow-up statement. Again, it's the same thing again and again and again. So I'm hopeful at this point you feel very confident with your interpretations. So with 95% confidence, we can safely say that the mean length of rivers will be at least 900 miles. Perfect. And that concludes practice number 10. Practice number 11 is exactly the same. So I'm actually just going to leave you with that to complete on your own. Okay. Other than that, we have completed our chapter 8 notes. So we still have 15 minutes left of class. So at this point, I'm going to still record because we are going to look at our first test. So I'm going to make a note of that when I describe this particular video. But if you have no questions on that test number 2, you're free to leave. But be sure to print out your chapter 9 notes, our last set of notes for Math 160. Excellent work, everyone. Fantastic. I will see you all on Wednesday.
Have a great day.
Thank you. Have a great day.
See ya.
Thank you.
Thank you.
You're welcome. I'm going to set these notes, put these notes together real quick while I'm at it. I will finish writing in the solutions for those 3 practice problems, which in the future I may just take out because they're very repetitive. Perfect. All right. So those of you who are here, you are here because you would like to look at your test number 2, and I would like to do that with you all. So who has questions that they'd like to go over first? Okay, so I'm going to share my screen for the Lumen test number 2. And we are looking at problem number 32. A population has parameters mu is equal to 203.6 and sigma is equal to 45. You intend to draw a random sample of size n is equal to 164. So we're essentially looking at the central limit theorem. We're looking at our unit 6 notes towards the end, right? Stephanie, what were you told about the mean of a population and the mean or the sampling distribution of sample means? Like what information do you know about those 2 things?
Wait, what'd you say? Sorry, my computer's has bad internet.
That's okay. I was just wondering, how would you answer what is the mean of the distribution of sample means? What do you know?
Well, I know the mean in the population mean is 65.4.
Well, in my case, it's what?
Oh, it's 203.6.
Good. So we learned that they're essentially the same, right? So if we were to take a look at our unit 6 notes towards the end, let me scroll up a little bit. You are told that the population mean, as you can see here, is equal to the mean of the sampling distribution of sample means. So they're equivalent. Now, the standard deviation for the sampling distribution of sample means is equal to the population standard deviation divided by the square root of n. So we're going to go to our previous page. Let's go to our previous screen. And it's asking for that particular standard deviation. So we're going to report our answer accurate to 2 decimal places. So we're going to take our population standard deviation, which is 45. And according to our formula, we are going to divide that by the square root of the number of items we have in our set, which is 164. So if you took 45 and you divided it by the square root of 164, you would get 3.51. So I'm going to write 3.51, and then we'll take a look. So the mean is exactly correct. They should be identical. Now for this one, it shows that we have 3.51, so we were exactly correct again. Any questions on that, Stephanie?
Yeah, I just got like, I don't know if I could share my screen with you, but
Yeah, sure. You can definitely do that.
I got like 1 place off. I don't know if that's,
Yeah, let me see. So you had 65.2 divided by the square root of 246. And I had 4.16 on my calculator.
oh, okay.
Yeah, I would just double check that to make sure that you punched in it exactly correct. It should be
Okay.
the standard deviation divided by the square root of n. Good. Very cool. What else would you all like to see?
If I can go.
Yeah.
Mine is 25, but I have a quick question on 22. I didn't want to take up time to rework this, but I have for the maximum usual 27 and the correct answer is 26. And I don't know if I did by a mistake or it was because I'm thinking it's so close. Like
Yeah,
Did
let me show you what happened here. So
Okay.
we know that to find, first off, we have to find the mean, right? Your average. So the mean is found by taking your n and multiplying it by the probability of success. So in this case, we know that our n is 69. There are 69 dragon eggs. And we also know that the probability that the eggs are yellow is 0.21. So that's the first thing we calculate. So 69 times 0.21 is going to give us 14.49. Perfect. Next, we are going to calculate the standard deviation. So the standard deviation, according to our notes for binomial distribution, is the square root of n times p times q. I'm going to write square root like they do in code, squirt. So we have square root of n is 69. P is 0.21, which means Q is going to be what's left over. So if you do 1 minus 0.21, that's going to be 0.79, the probability of success, the probability that it won't be yellow. So I'm going to take my calculator and type in the square root of 69 times 0.21 times 0.79. And that gives me an answer, standard deviation of 3.3834. We'll just do that. Now, to find the usual values, that range of lower and upper usual values, you always take your mean and you subtract 2 times the standard deviation. And then you take your mean and you add 2 times the standard deviation. Now, the important part to note here is that it wants you to give your answers as sensible whole numbers. So the first thing we'll do is figure out what that range is, and then we'll decide where to go from there. So our mean is 14.49, and we are going to subtract twice the standard deviation, which is 3.3834. When we punch this in, we find that the lower bound is 7.7232. We're going to do the same thing for the upper. So we have 14.49 plus 2 times the standard deviation, which means my upper bound is 21.2568. I'm going to write this in interval notation, 7.7232, comma, 21.2568. So this is the range of our usual values. One thing I want you to note, Surujni, is that 7 is outside of this range. 7 is below this range, which means 7 is unusual. I also want you to notice that 22 is outside of this range. 22 would be unusual. What that implies is that our middle values, the one that's just above our lowest and the one that's just below our highest, will be our minimum and maximum numbers. So I'm not gonna say 7 because 7 is outside of the range. I'm gonna say that the minimum number of eggs, excuse me one moment, let me get rid of this. The minimum number is going to be 8 and the maximum number is going to be 21 because 7 is too low and 22 is too high. And there you have it.
So that's why I have instead of, okay.
Yeah, you're off just by a little bit. It will
One.
only help to look at that range of values and then just write, what if it's too low? What if it's too high? What are the whole numbers outside of that range? And then you could say, well, it can't be those. It's got to be what's inside that range. Perfect. And it's only because it says, what is the usual number of yellow eggs? 7 would be unusual. 22 would be unusual because they're outside of that range.
Okay.
Beautiful. Very, very nice. You had also mentioned 25.
Yeah,
All right.
I just didn't know if anybody want to go before.
Is everyone okay with me looking at 25? Okay, sounds good to me. The Acme company manufactures widgets. The distribution of widget weights is bell-shaped. The widget weights have a mean of 56 ounces and a standard deviation of 5 ounces. So we're going to use the empirical rule. So the first thing we're going to do, and this might seem a little bit crazy, but I'm actually going to draw the normal curve on a separate sheet of paper. Because what I want to do with this is I actually want to label what my values are on that particular curve. So on a separate sheet of paper, and I'll show you my notes in just a second, I'm drawing my normal curve and I label the axis 0, 1, 2, 3, -1, -2, -3, just like we did before. You're told that the mean is 56 ounces and the standard deviation is 5 ounces. So I'm just going to stop the screen share for a moment, and I want to share with you my normal distribution. So this is what I've drawn so far. The next thing I'm going to do is I'm actually going to label each of these positions with its exact value. The mean is 56 ounces. One standard deviation above would be 56 plus 5, which is 61. Two standard deviations above would be another 5 added to that, so it's 66. And another 5 added to that is going to be 71. So far, so good?
Yeah.
We're going to go the opposite direction. So 56 minus 5, that's going to be 51. 51 minus 5 is going to be 46. And then 46 minus 5 is 41. So now I see the range of values here for my particular distribution. Let me share my screen with you for a moment, because I would like for you to see the notes for the empirical rule. So I'm going to scroll up until we find the empirical rule, and it's in our Unit 6 notes, because I think looking at this particular distribution with its percentages is going to be very, very helpful. I feel like that's on the first page. We're almost there. Here it is. So notice that from -3 to +3, according to the empirical rule, that accounts for 100% of our data values. So when we look at this question here, it says 100% of the widgets lie between. If we go back to our empirical rule, that's going to be between a -3 and a +3. According to what we drew here, that means 100% of the values are going to fall between 41 ounces and 71 ounces. Are you okay with that part so far?
Yeah.
Beautiful. So it's going to be 41 ounces and 71 ounces. Again, that's based on the diagram that we drew, and we labeled all of those. Now it says, what percentage of the widgets lie between 46 and 71 ounces? So I'm going to look at my diagram. So 46 and 71. So we want to go from a -2 to a +3. So we're going to go to our Unit 6 filled in notes. We're going to take a look at this empirical rule, and we want to go from -2 to +3. What we'll do here, Surujini, is essentially we're just adding these percentages up, right? We're just combining all of these things and getting a final total. So you could do this a couple different ways. One second, let me insert something here. If you notice that when you add these 3 values up, that's the same as 50%. Then all you'll want to do is you can say, well, let's take this 50% and add these 2 chunks here. So it's going to be 50 plus 34 plus 13.5, which gives us a percentage of 97.5. So what percentage? 97.5%. Take a look. There it is. What percentage of widgets lie below 61? So we go back to our diagram, and we want to know the percentage of widgets that lie below 61, which is a +1. So it's everything to the left here. So we'll go back to our Unit 6 filled in notes, which are right here, and we want everything to the left of a +1. So we're just going to add these percentages, or otherwise we could take this 50 and add the 34 here. So that's going to give us a total of 84%. Let's go back. 84% lies below 61, and there you have your solution.
Yeah, I realized what I did too. What I probably did, I didn't put the numbers at the bottom. I think I found for the first one, the -3 and the +3, and I fill in when I look on the table, I fill in what I found instead of putting the number that is the standard deviation. I think that's what I did wrong.
Okay, that makes a lot of sense.
Yeah, I went to the table instead of,
Instead of using the empirical rule.
yes,
That's okay.
yes.
That's okay. I see, that happens a lot, especially because we have something that's more accurate than the empirical rule, but they really did just want to use something super basic. They just wanted to use this basic stuff. Okay, where the mean is the center and then 1 standard deviation above, 2 standard deviations above, et cetera, et cetera, et cetera. Good, very good. I'm glad that was, that helped to kind of clarify things. Perfect. Thank you, Surujini.
I have questions. Actually, I
Yes.
have like 4 questions.
Yeah, awesome. Go for it.
First one is number 16.
Number 16. For the test, let's,
Yes.
oops, I opened up Firefox accidentally. Don't you hate when you accidentally click a button? You're like, no, I didn't mean that. Please, no. Let's get rid of this. Garbage. Okay. I do that all the time. All right, number 16.
So in the first exam, I got it right, but the second one, I just couldn't get it right. So what I did is, a die is rolled twice, and they're looking for probability of showing a 3 on first row and an even number. So what I did was, well, because I know there's 1 3, so 3 over 6, and then there are 3.
No. You just said there was 1 3 on a die. So how can it be 3 over 6?
Oh, maybe that's what I did wrong. So it was supposed to be 1 out of 6, and then 3 out of 6.
Yes.
Okay.
Yes.
Yeah, maybe that's, oh crap.
That's,
Okay.
that's okay. So when you do multiply these, you'll get 3 out of 36. And then of course, everyone, some of us, actually quite a few of us forgot to reduce, simplify these fractions, especially when it's requested. So this
So
is
that would be 1 out of 12. Yeah.
yes,
Crap.
yes.
I was like, how did I get this right? I first try it. How come I can't get it right? And I was so annoyed with myself. I just wanted to punch myself. Yeah.
Oh my gosh, no. No, never. But yeah, so it's the tiniest thing. That's all that happened. Just
I
be really
know.
careful. One
Yeah.
successful outcome out of the 6.
Yeah.
Good.
Um,
Next one.
my other question is 28B.
28B. Here we go. Yes. Okay, perfect.
So I got the A and C right, but B, I know I had that question before and I know I got it right, but I just, oh my goodness, I think I had a brain fart or something.
So it's interesting that they ask you part A first. So it says around what percentage of adults in the USA have stage 2 high blood pressure? So let's say, and I'm just going to show you, it's 3.39%. We go through the process, we find that it's 3.39%. Now I'm going to write a statement that says what we just found there. 3.39% of adults in the US have stage 2 high blood pressure. That's what we just found, right?
Okay, yes.
Now, I'm going to open this up because I want you to see this kind of clearly. Then it says, if you sampled 2,000 people, how many would you expect to have a blood pressure of greater than 160?
Yeah, so what I did was I multiplied by whatever number I got to the 2,000.
Yes.
Was that supposed to be the answer?
Yes. So let me show you how you do this. First, you turn 3.39% into a decimal. So it'd be 0.0339 because you have to move that decimal 2
Right,
over.
times by 2,000.
Yes. So let me punch this in. 0.0339 times 2,000, and that's 67.8. And then it says round. It says give your answer to the nearest person. Because I don't have 68 people, I would say 67 people.
Oh, you can round it to because it's 8.
It would accept it. They would accept 68.
Okay.
I have a feeling that
gosh.
if you put 67 or 68 it would accept. For me personally, when I look at a problem like this, I'm seeing that I don't have 68 people, but I do have 67, right?
Okay.
With this one, notice that the author said I had a bit of an issue rounding. So they were just saying try both, right? So
Okay.
I would put 67, you might have put 68, we'd both be right.
Okay.
Okay.
Yeah. See, I think I was having a brain fog. That's what it was. When I was taking my exam, I was tired. I don't know. I don't know what happened.
I get it. I get it. I mean, it's a
Oh,
grind, right? We only have 3, we literally have 5 more classes left.
yeah.
As crazy as that is.
So another question is, oh, before I forget, I know we're supposed to take our final on the 21st.
No, I think it's December 20th. That's a Tuesday.
Oh, okay. I'm going back home on the 20th. So I was wondering if I can take it before because I take my flight on
Let's
the
let's talk and find a date that would work for the both of us.
okay, okay,
Perfect. Yeah, you and I can talk about a good time.
okay.
Awesome.
So okay, does anybody have a question? Because I have 2 more.
Yeah. Oh, Stephanie says she has 29 and 31.
Okay, good, because I have 31 as well.
Yay. Okay, so let's look at 31 then first. A distribution of values is normal with a mean of 250 and a standard deviation of 24. From this distribution, you are drawing samples of size 31. So we want to find the interval containing the middlemost 30% of sample means. Good. The first thing we're going to do is we're noticing that we're referring to the central limit theorem, the sampling distribution of sample means. So I'm just going to show you my notes again. And we are going to look at the formulas. So if we scroll up, we see that we have a formula for finding the z-score of, I'm going to write this down, z is equal to the sample mean minus the population mean divided by the population standard deviation divided by square root of n. Okay, so that's the information that we are given in this case. We're told that the mean is 250. So the mean is 250. Which is the population mean, and the standard deviation is 24. From this distribution, you're drawing samples of size 31, so n is equal to 31. We want to find the interval, right? The interval of sample means, that means x bar is unknown, containing the middlemost 30%. Okay, check it out. Let's go over to my notes. We want the middlemost 30%. So the first thing I'm going to do is, oops, and I'm writing through my paper. I'm going to essentially note that I want the middlemost 30%. What that means is we need to find these values here. Okay, where 0 is in the center. We want to find the z-scores pertaining to these values. If the middlemost is 30%, what's left over?
60%. No, I'm sorry, 70.
And that means how much is in each tail?
35.
Yes. So the area, this is 35%, the area is 0.35. The area is 0.35. So we essentially want to know what is the z-score pertaining to an area below of 0.35. That's where we want to start. So I'm going to go ahead and look at my z-score table that's in my Unit 6 notes. It's at the very end. And we know that we're looking for a negative value. So negative value, and we're looking for 0.35. So 0.35, we're getting pretty close. It looks like it's right between these two values. Now we have to see which one we are closest to. So let's take 0.36317 and let's subtract 0.35. And I'm going to note the difference. And then I'm going to take, wait, what am I doing? No, what am I doing? Guys, you let me do this. You let me do this. Here we go. 0.35 is here. Wow, I can't believe I just did that. All right, so 0.35197, let's subtract 0.35. I'm going to write down the difference here. So 0.00197. And then I'm going to take 0.35 and subtract the 0.34827. I just want to figure out which one's closest. Do you guys see that it's closest to the right value? It's closer to the right than to the left. It's closer to this one here. So what we're going to do is we're going to look at the particular z-score at this position. And that's a z-score of negative 0.39. If you were to scroll up, you'd see that the column header is 9. So that refers to negative 0.39. Negative 0.39, which means the positive z-score is a positive 0.39. Stop me if that doesn't make any sense, okay? So we have our two z-scores. Now, keep in mind that we're being asked to find the range of sample means. We're being asked to find X bar. We have two different z-scores, so we need to find two different sample mean values. So we're just going to use our formula. So we have negative 0.39 is equal to X bar, we don't know what it is, minus the population mean, which is 250, divided by the population standard deviation, which is 24, over the square root of n, which is 31.
I have a question before we go on,
Yes, please.
so it can make sense. So anytime you have to find like the middle, and so if you find like this was 30 and one side is 35, and the other is that you find one, like you find the 35 and you get it's negative, you automatically know the other side would be positive. So
Yes.
whatever you found.
Yes, and that is because our normal distribution, that curve is symmetric about the
Mhm. Yeah,
So yes, absolutely.
thank you.
Good. You're very welcome. In the process of solving this, I would punch in my denominator. I did 24 divided by the square root of 31. And I would try to keep as much of it as I possibly could. And frankly, I can actually keep the whole thing. I'm going to write something down, but I'm actually not going to clear my calculator. I'm just going to write that down, but I'm not clearing my calculator, and I'll show you why. We don't have to clear it to write out, to do the math. Okay, so you see how I have my value in my calculator. The 24 divided by the square root of 31 is 4.31, et cetera, et cetera. The next thing I'm going to do is, aren't I going to multiply by negative 0.39? I'm just going to tell my calculator to do it. So times negative 0.39. Okay, and then that means this will be gone. My value over here will be negative 1.68, etc. And how do I get X bar by itself? By adding 250.
Add 250.
Yes, so I'm going to add 250 here, and I find my lower bound. So X bar, in this case here, for my lower bound, is 248.31889. I don't know what's around to yet, so I'll figure that out in a moment. Again, the same thing. Take your 24 divided by the square root of 31. We're going to multiply that by positive 0.39. And then I'm going to add the 250. So my upper bound here, X bar, is equal to 251.6811. Let's go over to our Lumen work. I'm going to open this up here. And it says, enter your answer using interval notation. Your answer should be accurate to one place after the decimal. So parentheses, we have 248.3, comma, 251.7. And that's what I had for my interval. 248.3 and 251.7. And you're done.
Oh, I see.
Not bad, right? I think a lot of it is keeping the value in your calculator so that you can be as accurate as possible.
I did that. Like, I did that, but I think my rounding was a little off.
Okay.
Yeah.
Okay. I definitely gave back credit, even if it was just a little bit of rounding error.
How are we gonna know that you gave us a credit? Like, for which problems do we go back and figure out? I mean, like, find out.
If you go to your grade book, you can actually look at your test.
Okay.
Yeah.
I think, oh, sorry, go ahead.
It's okay. So you go.
No, I think so I did that, and like I was trying to do it, and then I gave up because I felt like interval notation should be in that bracket. And when I tried to input the answer, I didn't see the bracket. So I figured I am doing something wrong, and I didn't put it in comma because if there's no way for a bracket, I thought I was doing it wrong. And I said, I don't know what else to do. Like, this is how you do it, but I don't have the bracket to put it. So it must be wrong.
Keep in mind, I know that's a little bit
That's what
tricky.
I did. Yeah.
Yeah, keep in mind for these with interval notation, because of rounding, it's actually safe to use parentheses. So we're approaching that value. That's essentially what that's saying. You're approaching that value, not including it. But it would have.
That's the bracket, right? That's the one like
No,
square.
parentheses are the one where you're approaching. the
Wrong. Yeah.
bracket is when you're including it.
Yeah. When I tried to input the answer, I didn't see bracket, and I thought I'm not doing it right. And
Dang it. Okay. No biggie. No biggie.
it's good. We're having this session, so at least you know.
Yes. Yes, I absolutely agree. Perfect. Let's take a look at, I believe there was a 29. So suppose that a brand of light bulb lasts on average 2510 hours with a standard deviation of 260 hours. So I'm going to write that down. So the average mu is 2510 and the standard deviation is 260. Assume the life of the light bulb is normally distributed. Calculate the probability that a particular bulb will last from 2091 to 3173 hours. So the really nice thing about this is that we are using our standard z-score conversion, right? We're not actually using the formula for the sampling distribution of sample means. So we know that our z-score formula is x minus the mean, the raw data minus the mean divided by the standard deviation. So what we're doing, Stephanie, is we're just finding the z-score for each of these, and we want to find the area within this range, right? So we see that our x for the first one is 2091. So we've got 2091 minus the mean, which is 2510, over the standard deviation, which is 260. I'm going to share my screen with you just so you can see. And we also know that z is equal to our x value, this second x value, that raw data value that we were given, is 3173. So 3173 minus the mean divided by the standard deviation. So we're going to find both of these z-scores. And as always, when we write our z-scores, we round to 2 places after the decimal. So 2091 minus 2510, divide that by 260. So our first z-score is a negative 1.61, 2 places after the decimal. Then we have 3173 minus 2510, divide that by 260, and we find that our second z-score is 2.55. Stephanie, what you're going to do is you're going to look up each of these z-scores, and you're going to find the area to the left for each one. Are you okay with the rest of this process, or would you like me to walk you through it?
I'm okay now. I think for the homework, I didn't really understand it. Then the test, I understood it.
Good. Okay, perfect. So yeah, you're just going to find the area of this region here. So find the probability or the area to the left, find the area to the left, and then subtract the 2 values. And that will give you the area between.
Okay.
Good.
So I didn't know you can actually see how long you spent like on a problem. And 31, I spent 45.3 minutes just because I'm looking for something that needs to go in bracket. Because if you look at the problem here, the answer, there is a bracket sign right there.
Yes.
So that was the problem for 31, like where you have to input the answer, there is a bracket sign, and that threw me off.
Yeah.
I don't know, can you, oh, if
I could-
you can see it there, but I can see it
is.
on
When
mine.
I click interval, so you see how you have two sets, you have basic notation and then you have interval. So
Yeah.
that's where it gives you the options. for
Oh,
what you
okay.
can use. You could use either of those. Notice it says in this context, either inclusive or exclusive intervals would be acceptable. So they would have accepted brackets also.
Oh,
Good. By the way, your brackets are on your keyboard. If you take a look at your keyboard, you'll see them to the right, and you can use those. as
yeah. But like when you're under pressure and you end up with this, like
I know.
it can be confusing. Like I just oh my gosh.
I totally get it. Good. We still have time for a couple more questions if anyone else would like to see any. If there are any other questions.
We just did 30, right?
We just did 31.
Oh,
I think we did 30, didn't we?
we did 29 here just now.
29.
Oh, okay. I was going to ask for 30. Is 30 similar to 31 or no?
No, they're so notice with 31, it asks for the middlemost 30%, right? So that middlemost 30%, that told you that the area to the left and to the right is going to be 0.35 because there's 70% altogether. This one's actually a little nicer to us, I guess, if you could say, because we want to find the height that separates the lower 60. So let me show you what that curve would look like, because I think, Donna, that's going to be really helpful to you. So we want to find the value that separates the lower 60. So let me I'll draw it here. I have room at the very bottom. So essentially we're going to take our curve and we're saying to ourselves, by the way, you know that if I drew a dotted line here and shaded this region, what percent of the curve would this be?
50.
Exactly. So we know that 60% is somewhere here. So we want to figure out what is that z-score that pertains to an area of 60%, which is, excuse me, the percentage of 60 with an area of 0.60. So that's when we go to our z-score table and we look for an area to the left of 0.60. And
where are we getting 60% from? I'm sorry.
That's from the actual homework question. That's from the test question itself. So notice it says, adult female height is normally distributed with a mean of 65.2 inches and a standard deviation of 2.34. What adult female height separates the lower 60%?
Oh, I was looking at mine because it says 26%.
Oh, well, that's okay, because it's the same exact concept.
Yeah, of course.
Good. So once you find the z-score pertaining to that value, that's when you're going to plug into your regular z-score formula.
And you subtract it, right?
Well,
No?
let's figure out what the process is first, right?
Okay.
We need a z-score first. So we want to look at the table and find, I don't know why it's doing this. We want to find the area to the left of 0.60. So 0.60 should be between these two. We have to figure out which one we're closest to.
So probably the 60.
Actually, it's closer to the one on the left.
Oh, really?
Yeah. I just subtracted real quick to check.
Do we always, a question on our test, do we always have to do that? Like, subtract which one is closer, or can we just like get the one that is the most closest, like 60?
Well,
Um,
this one isn't closer to 60 than this
No.
one. So you do have to test. You do have to figure out which one it's closer to. So it happened to be that it's closer to this value, which is a z-score of 0.25. So I'm going to write 0.25. So let me stop my screen share so you can look at my paper. We have the z-score formula. We now know the z-score, which is 0.25. We don't know the height of the adult female, but we do know the mean, which is 65.2, and that's from the problem. And we do know the standard deviation, which is 2.34. So Donna, all they want you to do is to solve that.
Oh, okay. I can go from there.
Perfect, perfect. That's
Thank you.
all they were looking for. You're very welcome.
Thank you so much.
Yeah, you're welcome. Awesome. Any last questions?
One, it's not about the test. So I have to get a new computer. This one shut down on me even on the test, which I'm grateful we had time
Yeah.
to do that. And like during Zoom sessions, like classes, I'll get knocked out completely and then get thing. I can't remember my Lumen sign in.
Oh,
If I have to use another one, is there a way I can?
no, I got you covered. That's easy.
Oh, thanks.
Awesome.
Because
Well,
I'm getting one today, but I was worried because I can't use the desktop downstairs because of Lumen. Like,
yeah. No, Surajni, your login name is just Surajni.
just that alone.
Yeah. And then I'm going to set your temporary password to password 123.
Just 1, 2, 3, nothing else, or do I have to put password 1, 2, 3?
Oh,
What is
yeah. Like literally, I'm going to type in the password
things?
in the chat. That's your
Okay.
password. So use that and then just change your password. But it is
Thank you.
just Surajni. That's your login.
Okay. Okay. And one more quick one. Do you know Professor Laura Bond?
I do, and she's fantastic.
So I'm on her waiting list for
Okay, so I know it's not a question, but it's more like a
Wait, can I interject? Does anyone have any last minute questions about the test that they'd like to go over?
No.
Okay, perfect. So this concludes our video for today. I will be uploading this, so please make sure you're watching, and I will see you all Wednesday for the start of chapter 9. Bye.